In this video, we find the Taylor series for a function, f of x, and I wanted to show you some examples where the center of the series was not 0. All of the series in the last video were all centered at 0. So this time we want to center our Taylor series for f of x at x equals 1. So remember what this looks like. Now with this one, there are no guarantees that this converges. So I'm going to use the tilde. We can try to prove convergence later once we talk about convergence more, but for right now, we're just trying to find the Taylor series for this function centered at x equals 1. So this is the nth term of the Taylor series is the nth derivative of the function evaluated at 1 divided by n factorial times x minus that center, which is 1, to the nth power. So if I expand this, I get f of 1 plus f prime at 1 times x minus 1 to the first plus 1 over 2 factorial times f double prime at 1 times x minus 1 squared plus 1 over 3 factorial times f triple prime at 1 times x minus 1 cubed, and you keep going. 1 over 4 factorial times the fourth derivative at 1 times x minus 1 to the fourth and we go on indefinitely. The nth term is the nth derivative at 1 over n factorial times x minus 1 to the nth. So again, it looks really bad. It looks like alphabet soup. You've got so much going on here, but it's really not that bad. There's only one unknown. The unknown is the nth derivative of the function evaluated at the center, n equals 1. So if I know what f of 1 is, that's a number, I substitute that in. F prime of 1, I substitute that in. F double prime of 1, F triple prime of 1. I'll just substitute in all of these values of my derivative. When I do that, when I'm done, I end up with this power series that represents, this power series, or this, corresponds to this function. Now this may or may not converge to this. If this function converges to a series centered at 1, it's going to converge to this one. But if it doesn't, then this is just a series that's generated by the function. It's a series that's associated with the function and generated by the function by taking its nth derivative and plugging in 1 and substituting. So there's no guarantee of convergence here, but these guys are connected. This is the Taylor series for that function. All I have to do is find the nth derivative and plug in 1, and then substitute those in here, and the 1 factorial, 2 factorial, 3 factorial, 4 factorial, all of that, that just depends on the term. The only unknown is our nth derivative. So let's write f of x differently. We've got f of x equals 4 times 3 plus 2x to the negative 3. I'm writing it that way so that it's a little bit easier to see the pattern. And now I want to find a pattern for the nth derivative. Now when you're doing this, you don't want to simplify. Pretty much leaving everything expanded is a good idea, unless you are repeatedly multiplying by the same number. Then that's like an exponential term. You might want to write that exponential factor as an exponent. But if you're not multiplying by the same number, if you're seeing a factorial type pattern, you need to keep that in there. You need to leave it expanded. That way you can see the factorial as it's evolving. So let's take the first derivative. So I've got a 4 there. And the derivative of this, well, that requires the chain rule. Here's my inside function. The derivative of a function raised to some power is that power times the function raised to the 1 less power. So you put the inside function back in, and then you subtract 1 from the exponent, and then you multiply by the derivative of the inside by the chain rule, which is 2. So notice it started positive, now it's negative, and now let's take the derivative again. So I still have that 4 there. When I take the derivative again, I get negative 4 times negative 3 times 3 plus 2x to the 1 less power, that's negative 5, times that 2 from before, times an extra 2 by the chain rule. So I'm just bringing that 2 down, times the derivative of the inside is another 2. So I think I'm going to keep multiplying by 2. Every time I take the derivative of the inside, I multiply by another 2. So I'm going to simplify this. I'm going to call that 2 squared and keep that in mind. Okay, let's take the third derivative. Bring the 4 down. We've got negative 4 times negative 3 times negative 5. Oops, maybe I should have written that, in a different order. I will in a second. And then I've got this to the negative 6 times the 2 squared times the extra 2 by the chain rule. Let's write this in the right order. I've got the 4 from before, and this is negative 5 times negative 4 times negative 3. And then we've got the 3 plus 2x to the negative 6, and 2 squared times 2 to the first is 2 cubed. And let's do the fourth derivative, and then we'll try to find the pattern. Bring the 4 down. The derivative of this is going to give me a negative 6 out front. So I have negative 6 times negative 5 times negative 4 times negative 3 times 3 plus 2x to the 1 less power, that's negative 7. And then we'll have the 2 cubed, which we had from before, times an extra 2, so that'll be a 2 to the 4th. Okay, so the first thing I do whenever I'm looking for a pattern is I think about what all of these guys have in common. What is staying the same? Well, it doesn't matter which order derivative we're looking at. I've got a 3 plus 2x in parentheses. So I can write that down. Notice they also have a 4 in common. Well, and that's because of the function, there was a 4 in the numerator. So that 4 is going to be in all of those derivatives. So we have a 4, and then we have this 3 plus 2x raised to some power. And notice all the powers are negative. Okay. Now I want to look at the relationship. Oh, also, another thing. Notice that we've got a 2 here. With f prime, I've got a 2 to the first. F double prime, I've got another 2, but it's squared. When f triple prime, I've got a 2 cubed. The fourth derivative, I have 2 to the fourth. So I've got a 2 to some power. And then this expression that's out front, it changes a little bit. But it reminds me of a factorial. So I'll come back to that in a little bit. So we've taken care of everything that stays the same. Now we want to think about what changes as you go from term to term. Well, for the 0th derivative, this is a negative 3. For the first derivative, that's a 4. For the second derivative, that's a 5. For the third derivative, that's a 6. Fourth derivative, that's a 7. I hope you see that there's a pattern there. Whatever the order of the derivative is over here, that number is 3 more than that if I ignore the sign. So if that's a 4, 4 plus 3 is 7. 3 plus 3 is 6. 2 plus 3 is 5. And it actually makes sense because I started with a negative 3 here, and then I kept subtracting 1 every time. So that initial negative 3 should be there. When there's 0, I haven't done anything yet, so it's still a 3. Say, okay, well, what was that again? Let's look for the pattern. What's the relationship between the order of the derivative and that exponent? Well, if that's a 1, that's a 4. If that's a 2, that's a 5. If that's a 3, that's a 6. So if I add 3 to all of the orders of the derivatives, I get those numbers. So if this is an n, this is going to be n plus 3. Now let's look at the relationship between the order of the derivative and the power of 2 over here, this blue highlighted 2. For the fourth derivative, I've got a 2 to the fourth. For the third derivative, I've got a 2 cubed. Second derivative, 2 squared. First derivative, 2 to the first. Over here, there's no 2, but couldn't I call that a 2 to the 0? I think I could. Since it's the 0th derivative goes with 0, the order of the derivative and the power of 2 are the same, and that makes sense because that 2 came from the chain rule. Every time I took a derivative, I had to multiply by an extra 2. So if this is the nth derivative, that's a 2 to the n. Okay, so we've taken care of all of that. Now let's focus on this part that I have not highlighted. It looks a lot like a factorial. We also have an alternating sign. Well, let's take care of the alternating sign first. That's either a -1 to the n or a -1 to the n plus 1. I think it's a -1 to the n because the 0th derivative starts positive. So -1 to the 0 is a positive 1. -1 to the first is a -1, and the first derivative is negative. Second derivative is a negative times a negative, so it's going to be a positive. So it's a -1 to the n for the alternating part. And now let's look at the relationship between the nth derivative, the order of the derivative, and this factorial type expression over here. I've got 6 times 5 times 4 times 3 when that's a 4. It's almost a 6 factorial. There's a 2 missing, but it's almost 6 factorial. And then I've got a 5 times 4 times 3 when there's a 3 there. Almost a 5 factorial, but there's a 2 missing. And that's almost a 4 factorial, but there's a 2 missing. And that's almost a 3 factorial, but there's a 2 missing. And that could have been a 2 factorial, but there's a 2 missing. So it's like we've got factorials here, but they're missing this extra factor of 2. Watch this. In order to make it the factorial that I need it to be, I'm going to multiply everything by 2. And that's legal as long as I also divide by 2. You're saying, does that even do anything? It does, because now I've got a factorial and an extra 2 in the denominator, and we're cool with that. That's great, because now I can write that as a factorial. So this is a factorial, and then we've got an extra 2 in the denominator. So I'm going to put the divided by 2 here. Now let's think about that factorial. When this is a 4, we've got a 6 factorial. When that's a 3, we've got a 5 factorial. Well, the relationship between 4 and 6 is that 6 is just 2 more than 4. So if this is n, I think that's an n plus 2 factorial. Let me write that down, and let's check it out. When I have a 4 here, I've got a 6 factorial. Good. What's 2 more than 3? 5. Do I have a 5 factorial? Yes. What's 2 more than 2? 4. Do I have a 4 factorial? 4 times 3 times that extra 2 I had to multiply by? Yes. When I have a 1 here, do I have a 3 factorial? 3 times 2? Yes. I have a 0 here. Do I have a 2 factorial? And I multiplied by the extra 2. I forgot to do it for that one. Yes, it works. So this is our pattern for the nth derivative. Now, remember what we're trying to do. The goal is to find this Taylor series. So what we really need is not the nth derivative evaluated at x. We need the nth derivative evaluated at 1. And then we're going to substitute that in and simplify, and that will be the Taylor series for this function. So let's evaluate this at x equals 1. And we can also simplify a little bit, that 2 to the n over 2 to the first. Because of this property, we can subtract the exponents. Oops, I want to evaluate this at x equals 1. And actually, if we wanted, we could call that 4 at 2 times 2 and reduce one of those 2's with that guy down there. Okay, so I've got 2 to the n times a 2 to the first is 2 to the n plus 1. A -1 to the n plus, or -1 to the n, and then an n plus 2 factorial. Now this is the only part that has an x in it, and we've got an exponent of -n plus 3. So we're going to have 3 plus 2 times x to the positive n plus 3 in the denominator, if I move that down to the denominator. I'm replacing the x with a 1, and I get that. So I've got 2 to the n plus 1 times -1 to the n plus 2 factorial, and 3 plus 2 is 5, so that's 5 to the n plus 3. Okay, we're not done yet. I know it feels like we're done. We're like, yay, we got the nth derivative of the function at 1, and it's really exciting, but we have not found this guy yet. So our goal was to find the Taylor series, so we need to substitute in up here. Okay. So f of x is 4 over 3 plus 2x raised to the third. That corresponds to this Taylor series. And we're replacing the nth derivative of f at 1. We're replacing that highlighted function with this. Now, since it's a fraction, I can write it this way. I'll have 2 to the n plus 1 times negative 1 to the n times n plus 2 factorial. All of that is divided by 5 to the n plus 3. And that's all being divided by n factorial, but dividing by n factorial is the same as multiplying by 1 over n factorial. So this is the nth derivative at 1 divided by n factorial. Don't forget this part, times x minus the center of the series raised to the nth. Now this is our solution. It's just not simplified. The n plus 2 factorial and the n factorial can be simplified a little bit. N plus 2 is larger than n, so I can expand that. So I'll expand until I get an n factorial. I do n plus 2, 1 less than that is n plus 1, 1 less than that is n factorial. And the n factorials reduce. So we have our final answer. I don't want to use another sheet of paper for it. I'm just going to write it right here. The Taylor series for 4 over 3 plus 2x quantity cubed is this. Here's the simplified version. The sum as n goes from 0 to infinity of 2 to the n plus 1 times negative 1 to the n times n plus 2 times n plus 1, all divided by 5 to the n plus 3. Those are the coefficients, times x minus 1 to the n. That's what we were looking for, the nth power.